Although Albert Einstein is regarded as one of the most brilliant scientists to walk the planet, he was a human just like the rest of us, and even made some mistakes. Here are 5 of the biggest errors made by Albert Einstein in his scientific life. Albert Einstein denied the existence of black holes, even though the idea of black holes originated from his general theory of relativity. With general relativity, Einstein changed the course of physics. The theory describes gravity as a curvature in the fabric of space and time rather than a force, as proposed by Newton in the 17th century. Through general relativity, Einstein developed the field equations that relate the geometry of space-time to the distribution of matter contained in it. But a German physicist named Karl Schwarzschild found something strange hidden in those equations. He became the first person to find an exact solution to the field equations which describe the gravitational field around a non-rotating spherical mass. He found that there exists a radius for a given mass where if the mass could be compressed to fit inside that radius, no known force or degeneracy pressure could prevent it from continuing to collapse into a hole, also known as a gravitational singularity, or later, a black hole. This meant that space-time would dramatically break down at a gravitational singularity, into which even light would inevitably fall. In 1930, Indian astrophysicist S. Chandrasekhar discovered that if a star were more massive than a specific limit, known as the Chandrasekhar limit, the star's core would collapse to form a black hole. But Einstein could not wrap his mind around this idea of gravitational singularity. Subsequently, in 1939, Einstein published a paper in which he rejected the concept of black holes by making various assumptions that were later proven to be false. In his paper, he wrote that Schwarzschild's singularities do not exist in physical reality. But today, besides plenty of indirect evidence of their existence, we have the images of 2 supermassive black holes that verify our current understanding of these objects. So this means that Einstein was wrong about black holes, and that such exotic objects do exist in the universe. In the early 20th century, Einstein and many astronomers believed that the universe was static, but this idea didn't align with his general theory of relativity. Instead, his equations predicted a dynamic universe. So to achieve consistency with the prevailing views, in 1917, Einstein introduced a new term to the field equations, the cosmological constant. This constant ensured that Einstein's math and general relativity and other terms in the field equations were unaffected by the assumption of a static universe. But a decade later, when Edwin Hubble discovered that the universe is expanding by studying the velocity and distance relationship of galaxies outside the Milky Way, Einstein abandoned the static universe model and proceeded with his original idea of a dynamic, expanding universe. In later years, Einstein called the introduction of cosmological constant the biggest blunder of his life. However, now it is a well-known fact that the universe is not only expanding, but also accelerating in expansion. In modern cosmology, the meaning of cosmological constant has been changed to represent dark energy, which disturbs gravity and does not balance it, causing an acceleration in expansion. Everything is certain regarding classical physics, such as Newtonian gravity, general relativity, and electrodynamics. In Newtonian physics, for example, if you know the position of a particle as a function of time, you can determine its velocity, acceleration, momentum, and energy with certainty using simple laws of motion. But quantum mechanics, the study of motion and interaction of subatomic particles, is based on the probabilistic nature of particles. Quantum theories say that it is only possible to compute the probabilities of an event happening rather than obtaining a definite result. Albert Einstein was one of the founding fathers of the old quantum theory, the collection of results from the first 25 years of the previous century. He won the 1921 Nobel Prize in Physics for his discovery of the law of the photoelectric effect. But Einstein was never convinced by the new quantum theory. Ideas like Born's rule of probabilistic interpretation of a quantum system, Bohr and Heisenberg's Copenhagen interpretation, Schrödinger's cat thought experiment, and the uncertainty principle made quantum mechanics look weird. He was never impressed by these principles of the new quantum theory and said that there could be a better way to work around the subatomic world. In a letter to Max Born, he once wrote, "God does not play dice with the universe," implying his refusal of the randomness offered by quantum mechanics. But today, these complex principles lie at the heart of quantum theory. We have built quantum computers, achieved quantum teleportation, and developed electronic devices that use quantum mechanics as we know it. Gravitational waves are a direct consequence of Einstein's theory of general relativity. They are the ripples in the fabric of space-time caused by massive accelerating objects, such as black holes and neutron stars, locked in a binary orbit. Even though they are an outcome of general relativity, Einstein got cold feet about their existence and believed they were impossible to detect, as he also doubted the existence of black holes. He even submitted a paper in 1936 proving the non-existence of gravitational waves, but it was rejected, pointing out the possibility of a mistake. The first proof of their existence came in 1974 through their indirect observation by studying the behavior of binary pulsars, which was consistent with the prediction of general relativity. Direct evidence of their existence was obtained in September 2015, when LIGO detected these waves generated by two colliding black holes, 1.3 billion light-years away. Although we cannot regard this one as a mistake, Einstein could never develop the theory of everything. The theory of everything is a holy grail of modern physics. It is motivated by the idea that a single theory governs nature at all levels. According to this idea, all four fundamental forces in nature, gravitational force, electromagnetic force, strong force, and the weak force, unify. Albert Einstein spent the last 30 years of his life working on developing this unified theory. In particular, he was interested in finding a way to combine gravity and electromagnetism into a single theory. He believed that the unified theory had to have quantum mechanics as a consequence, and he was always unpleased by the randomness and unpredictability of quantum mechanics. He became more focused on mathematical arguments rather than following the physical sense that led him to his significant discoveries in his youth in this quest. But Einstein never gave up his search for the Holy Grail. He continued his work even on his deathbed. Though his work on unified theory did not produce a result, Einstein emphasized unification as the ultimate goal of physics. And even today, he is an inspiration to many scientists who have devoted their careers to developing the theory of everything. No number of mistakes can outweigh Einstein's extraordinary accomplishments in physics and his contributions to our understanding of the universe. As he once rightfully said, "A person who has never made a mistake has never tried anything new." He was only a human in making these mistakes. His work has inspired many generations to take up physics and make a difference. And the fact that he did not abandon physics until his death, despite his mistakes, is a testament to his sheer intelligence.